In this tutorial, we will be discussing colligative properties and osmosis. Adding a solute to a solvent modifies the properties of a pure solvent. These changes in pure solvent properties are referred to as colligative properties. Colligative properties depend only on the number of the solute particles relative to the solvent particles in solution, and not on the type or the kind of solute particles. Some examples of these are Raoult's law, which discusses the vapor pressure decreasing over a liquid; melting point depression, which indicates that the temperature of the melting point will actually decrease; and boiling point elevation, the temperature of the boiling point increases. Not listed among these is osmosis. Osmosis is when the semipermeable membrane allows only the movement of solvent molecules. Solvent molecules move from the pure solvent to solution in an attempt to make both of the same concentration of the solute. So if we look at this picture down here, we have a more concentrated solution on the left-hand side and no solute particles on the right, meaning that there is no extra things in there. This is a semipermeable membrane. This allows some particles to pass through and others to not. So for instance, the water molecules can go through it, but these solvent particles, the things that are dissolved in here, cannot because it's too big. So what the water is going to do is it's going to try to push its way through and make this more dilute on the left hand side. So if you look at the picture on the right hand, the picture of the solution went up, where the side with the water went down. That's because the water went from the right to the left, trying to dilute out these particles. Now remember, it's not always going from the right to the left. You're going to want it to go in the direction that's more concentrated, and that's the more important takeaway message here. And then finally, the solution stops trading places and it forms an equilibrium here, where they're both coming and going at the same rate, and that's because the osmotic pressure of the solution. It's the pressure of the excess fluid. It's right here. The driving force for osmosis is entropy. The osmotic pressure counterbalances pressure of solvent molecules moving throughout the semipermeable membrane. And we have this equation so that way we can solve for it. So pi here is the osmotic pressure. M is the molarity of the solution. R is the ideal gas law constant. This one's given to you in atmospheres. And T is for temperature in kelvins. Make sure it's in kelvins because it has to cancel out with the ideal gas law. So let's do a practice problem of these. A 35-gram sample of hemoglobin is dissolved in enough water to make a 1 liter solution. The pressure is measured to be 10 millimeters of mercury at 25 degrees Celsius. Calculate the molar mass. So essentially what we're going to need to do at the very end is make sure we have grams per mole as in the calculation. But in order to do that, we need to use the osmotic pressure. So the osmotic pressure is equal to the molarity times R times T. So this is a pressure, but R is in atmospheres, so we need to convert the 10 millimeters of mercury over to atmospheres. Make sure your units for R matches up with the other units in the equation. 760 millimeters of mercury are in 1 atmosphere. Divide that out, and it comes out to be 0.0132 atm. While we're at it, why don't we go ahead and convert our 25 degrees Celsius by adding 273. That comes out to be 298 Kelvin. So the pressure is 0.0132 atm. I'm not going to solve for the molarity yet. That's what I'm actually going to be solving for in the equation, because from the molarity we can get the moles. That's our goal. We have the liters of the solution right there. times the ideal gas law, liters, atmospheres, that matches up with those atmospheres, moles, the moles and liters match up with the molarity, in Kelvin, which is what we're about to add right here, 298. Multiply and divide and solve for M. And M comes out to be 5.40 times 10 to the negative 4 moles per liter. From here, I know that the molarity equation is moles over liters. That means I can determine what the moles are. So I know what the molarity is. I'm trying to find the moles. The liters of the solution is just 1. Cross multiply, and I know I have 5.40 times 10 to the negative 4 moles here. Now I'm looking for the molar mass, which is grams per mole. I know how many moles we had in there, and I also know how many grams we had to begin with. So I can divide these two to figure out the molar mass. And that gives us 6.49 times 10 to the 4th grams per mole. And that's how you use osmotic pressure.